Right, in this video, I'm going to be talking to you a little bit about slope fields. And this is kind of the start of our unit on solving differential equations. In the previous unit, we studied differential equations, but we kind of just always went and took more derivatives. And in this unit, we're going to start to look at how can we recover a function based on information about its derivative. And so we talked about differential equations last unit, but I never really defined them. A differential equation relates a function, like the value of y, its independent variable, which in this class is generally x, and its rate of change, which we have been calling dy dx. And a slope field is a graph of a differential equation. So if we want to sketch the slope field for a differential equation, we're going to usually just make a 3-column chart. But one thing I want to point out right now, just before I even really start in on this, is the fact that dy dx depends only on x. So I really don't need to have the y numbers in there. And it's a lot of points, between x equals -2 and x equals 2, with y being also between -2 and 2. It's a lot of, points to plot. So I'm going to just only consider in terms of x, right? Because dy dx only depends on x. Okay, so when x is 0, dy dx is going to be 2 times 0, which is going to be 0. And y can be whatever it wants. So any place where x is 0, the slope is 0. And we know what slope equals 0 looks like. It's kind of flat. And so what I'm going to do, I'm going to just draw a little horizontal tick mark. And that's how we draw these slopes, is we just draw little tick marks. They're giving just a general idea of what the behavior of the function is at that point. Okay. Where x is equal to 1 and 2, dy dx will be equal to 2 and 4, because dy dx is just 2 times x. So then I'll go in and I'll make a slope of 2. Now we know that a slope of 2 kind of looks like this, right? Over 1 up 2. But if I was to take that length of tick mark and put it over there at the point 1, 0, I would just have like way too much red on the page, really. And also just get too crowded. So what I'm going to do is I'm going to just start here at the point 1, 0. And I'm going to aim for this, right? That point up there that's over 1 up 2. But I'm not going to go all the way, right? I'm just going to aim towards it, go forward, go backward a little bit, and that'll be a decent tick mark. And then I'm just going to kind of keep doing the same thing. That one I was aiming at this. This next one I'll be aiming one above, and just trying to do the best I can. These don't have to be perfect. And we need that down here and over here also. All right, and dy dx equals 4. That's a very steep slope. And so nobody's going to come and measure your tick marks with a protractor to make sure that they are, the appropriate angle against the horizontal, right? We just need to make sure that dy dx equals 4 represents a definitely steeper slope than dy dx equals 2. Okay. So over here, where x is equal to -1 and -2, we're going to see pretty similar things. It'll be -2 and -4. So we can do that. And then -4, that's very steep. So you don't want it to be vertical, but you want it to be pretty close to vertical while still being negative. Okay? And I am recording this not with people in my room, but if this were, live in class, what I'd ask at this point is, anybody see kind of like a pattern emerging from the slope field? And what I want you to see is that it kind of looks like a family of parabolas. That, if I was to sketch a curve that fit these kind of specifications, well, it sure looks like y equals x squared. Okay? And then I also want you to notice, if you have y equals x squared, then you know that dy dx is equal to 2x. Okay, so y equals x squared is what we would call a solution to the differential equation dy dx equals 2x. Okay? It's actually a particular solution because if you think about it, if I did y equals x squared plus 8, dy dx would still be equal to 2x. If I did y equals x squared minus 100, dy dx is still equal to 2x. So we'll say that in general, the general solution to dy dx equals 2x is going to be y equals x squared plus c, where c is just any old number. And that's why we see that, there could be, kind of vertical shifts on this parabola, and we'd still be fitting in with our slope field. Now I'd like you to try this on your own. So I want you to try to sketch a slope field for dy dx equals y. And I'm going to pause. I'm going to just fill in the slope field, and then it's just going to come up in like 5-10 seconds. So you should definitely pause, work it yourself, and then check in against my answer. Okay, there you go. So what I did, I said, okay, over here, dy dx only depends on y. So wherever y equals 0, dy dx is going to be 0. Where y equals 1, dy dx is 1. Where y equals 2, dy dx equals 2, and so on, right? And then, typically, if there were people in my classroom, I would ask, okay, anybody see the pattern on this one? And this one's a little tougher to see the pattern for sure. The pattern that is happening here is it's exponential. And probably if I had made this a window that just started at y equals 0 and went up to like y equals 4, then maybe you would see the pattern a little quicker. But I think it's good that we see both sides of the x-axis for this one because of the nature of the general solution to dy dx equals y. Okay. I'm going to say, all right, hey, look, here's a curve. I know that at least here it's going to have that slope, but it looks like, as I go up, I'm getting a steeper slope. And then as I go to the left, I'm getting a shallower slope, right, because I'm going down. Wait a second, I've seen this curve in this class before. This is the graph of y equals e to the x. Okay. And because we know that if y equals e to the x, then dy is also equal to e to the x. So dy dx equals y. But you're like, wait, what's going on down below the x-axis? Or what's going on the x-axis even? I might, in gray, go over here. I don't know if this is going to work or if it's going to end up going behind the colors, but let's talk about the curve in gray, because it seems to be fitting the slope field. That's the curve y equals 0. And if y equals 0, we know how to take the derivative of 0. The derivative of 0 is going to be 0. And if dy dx is equal to 0 and y is equal to 0, then we are fitting the description of dy dx equals y. And fitting it kind of in a trivial way, but we are still fitting. Okay? And then down here, down below the x-axis, and this is probably not, that's not as good of a curve, but whatever, I tried. Y equals negative e to the x. Well, that would give you dy dx equals negative e to the x. So really what the general solution is going to be to this one, for reasons that you just don't know about yet, is going to be y is equal to any number times e to the x. Even 0, right? C equals 0, that's the curve in gray. C equals negative 1, that's the curve in green, and C equals 1 is the curve in blue. That's going to be the general solution. But we'll talk a whole lot more about that in the videos to come. And now another thing before I move on, that I feel like I've mentioned this word but didn't really define it, is that a solution curve to a differential equation, a solution to a differential equation, has an equation that satisfies the differential equation. It has the derivative that matches the pattern, right? So like y equals e to the x, y equals negative e to the x, y equals 0. Those are all solutions to the differential equation dy dx equals y. Right, now, for AP Calculus, the things that we need to be able to do with slope fields are actually quite limited. Okay, there's only really 3 things we need to be able to do. We need to be able to sketch the slope fields kind of like we did before. We need to be able to sketch solution curves, which is kind of what I was doing in blue up above earlier. But we won't ever have to do that on a slope field that we created ourselves. Okay? On the College Board items, they will either ask you to sketch a slope field or they will ask you to sketch a solution curve to a given slope field, but they won't ask you to produce a slope field and then sketch a solution curve. That's too much to grade. So when we sketch a solution curve, what we're doing is we're just following the lay of the land, right? We're just kind of in general following the pattern. Now, this one right here, that's one in my class proposed that possibly the one that goes through 0, 1 is actually a straight line. Okay, and I think that actually might be true. I'm not sure. But what I'll say is that will be a suitable curve for us, because the standard for the grading and the free response, I graded one of these this summer, The standard is that it needs to go to the edges of the window, like to the edge of the slope field. Your curve needs to extend in both, or all the way to the end. But it also just can't have any like horrible, flagrant contradictions to the slope field. And by flagrant contradictions, we pretty much meant like increasing when the slope decreasing, or continuing to increase through a flat tangent or something like that. That was what we considered flagrant. So although this curve is not perfect, it doesn't line up exactly with all of the tick marks. It's not horrible either, and therefore it will be good enough. Okay. And then this one, I can see that it's going to go kind of up and then down, And what I've found is with the sketching of the solution curves to the slope field, is that the harder you try on these, the worse the product looks. So you need to just kind of take a step back, look at the general pattern, use a pencil so that you can erase if it's horrible, and just take a step back and look at the general pattern and then just try to mimic the pattern. Don't try to jump from tick mark to tick mark. That just doesn't work. And if you do just try to jump from tick mark to tick mark, your curve will look really robotic. It won't look curved at all, and it just, like I'm saying, it'll look worse than if you just kind of say, it just goes up, down, and I'll just do that. Okay, consider the slope fields below. I'm going to want you to write the differential equation for the slope field and sketch the solution curve that passes through 1, 1. Okay, realistically, A is probably not a question you're going to be asked, on an assessment. That's just a little beyond the scope of what we do in this class. But I think that, with a little bit of guidance, that we can figure out an equation for these. It does sure look to me like over here where y equals -1, we're going to have flat slopes because it goes from positive to negative as I move down. But what I really want to point out about this one is that as I move left and right, as I manipulate x, I'm seeing no change in the slope on that row or on any of the rows, right? As I go left and right, I'm not seeing any change in the slope, which is telling me that, let's see, I think I used blue on the first one. Over here, this is telling me dy dx is independent of x, right? Because it doesn't change when I manipulate x. So I'm just going to say it depends on y only. And then, I'll work the one on the left first all the way through, and then I'll touch the one on the right. But while I'm talking, I could point out that if I look left and right on this one, I'm seeing different slopes, okay? But if I look vertically, if I look along a column, any particular column, I'm going to get the same slopes everywhere. Okay? So I'm proposing that this means that dy dx depends on x only. Okay. Now I'm going to go flip back to, a couple pages before. And ask you to notice that we've actually already seen this happening. In this first slope field that we drew, dy dx only depended on x. So as we moved left and right, we saw different slopes, right? And it depended on x. But vertically along a column, we were always having the same result, right? And that's why we didn't really care what y was over here, because dy dx only depended on x. And then for the second curve, or for the second slope field that we drew, look and see that, as we move left and right, we're seeing this time. Okay, so manipulating x, getting the same slope back must not depend on x. But as I look on a column, I'm seeing different slopes, and we see also that dy dx depends only on y. Okay. So that's a really useful trick or technique to eliminate answer choices, especially in a multiple choice setting. Okay, so back to these. If dy dx depends on y only, and this looks a whole lot like the slope field for dy dx equals y, except for at y equals -1, the slope is 0, and at y equals 0, it sure looks like the slope is 1, just based on, kind of extending one of those tick marks. So I think that if the slope is equal to 0 when y is -1, I feel like y plus 1 could be a potential candidate. And then you look at where y equals 0, the slope is 1, that fits. where y is more negative than -1. I'm getting a negative slope. It depends only on y. I think that's going to be it. And then over here, this one that depends on x only, okay, I'm seeing a couple of things. I'm seeing on the right half where x is positive, the slopes are positive. Okay? And on the left half where x is negative, I'm seeing the slopes are negative. Moreover, I'm seeing that when x is getting larger in either direction, the slopes are getting flatter. Alternatively, I could have said that the closer I get to the y-axis, the steeper the slopes are getting. But the bigger that x gets, the smaller the slope is, right? So I think the most obvious relationship is 1 over x that mirrors that, right? The bigger x is, the smaller the result is. And the closer x is to 0, the larger the result is. And it also fits with x being negative, slope being negative, x being positive, slope being positive. So dy dx equals 1 over x is going to work for this one. But again, just in case you didn't hear me the first time, I won't ask you to just come up with an equation out of thin air for a slope field. That's not something that you need to do in AP calculus. But it says sketch the solution curve that passes through the point 1, 1. That is something we definitely need to be able to do. So I'm just going to kind of plot these 2 points. And, all right, see that it's kind of leveling off, and we know we need to go to the edge of the field. Okay, the fact that it's getting steeper and steeper near the y-axis does tell me that I feel like, you know, we're going to have like vertical slopes here. If there was a curve that, that didn't go well. If there was a curve that fit that. We actually know of a function that has derivative 1 over x, and, well, it has a vertical asymptote at x equals 0. You're thinking about that. Hopefully you're thinking about that and saying, oh, what function is that that has dy dx equals 1 over x? And this is not that curve, so I'm going to kind of write it in a different color. You know, one example of a function that would have dy dx equals 1 over x is y equals natural log of x. But if you think about it, there are others too. So I might just let you think about that, which others there are. And I almost forgot to sketch the solution curve for the one on the left, but it's just going to kind of be, you know, some kind of an exponential growth situation. I'm going to go to the edges of my field always and, you know, just follow the lay of the land. That's the best advice I can give you. Now, the last thing I got for you in this video is match the slope field to the equation. This is a multiple choice task. And what I'm thinking, oh yeah, I remember what I was doing here, is I'm going to encourage you to just try to, you know, make your eliminations based on, depends on x, depends on y, and then maybe 0 slopes past that. So if I move side to side here, I'm seeing different slopes. So that's telling me that dy dx has to at least depend on x. So I can eliminate answer choice C, right? But then if I go up and down, I'm also seeing that it's got to depend on y because I'm seeing different slopes. And so I need my equation, my differential equation, to depend on both x and y. So that's why I'm just going to say it's dy dx equals x minus y. Now, it probably won't be that easy for you on like a test or on the AP exam or something like that. But we can almost always eliminate like at least one answer choice. And so I'm going to do the same thing over here. Look, I'm seeing different slopes as I manipulate x, and I'm seeing different slopes as I manipulate y, so it's got to depend on both x and y. Okay, so I'm going to, based on that, eliminate answer choice E. And then I'm going to think, what's the next thing I notice? The next thing I'm noticing is that I've got this whole column of dy dx equals 0. So I'm going to say, if x equals, it looks like -1 to me, then dy dx is equal to 0. Right? So that's going to eliminate this one, because if x is -1, then dy dx equals -y, and that's not guaranteed to be 0 for every y. Okay. What about this one? B, that's also not going to work, because I'm going to have -y minus y would be -2y for dy dx. That's not always 0. And then For C, I think this one's going to work because if x equals -1, then dy dx equals negative y plus y, which is equal to 0, which is kind of what I had kind of set out to find. What's wrong with D? Oh, if I plug in x equals -1, then I get negative y minus 1, which again is not guaranteed to be 0. Right? It can be 0 sometimes, but not always. And so that's why it's answer choice C. You can also use this row of 0 slopes, which I will say, if, well, no, that's not x, that's if y equals 0 on the x-axis, then dy dx equals 0. That would pretty much only help you eliminate answer choice D, though, because the rest of them, yeah, and that's just, having already eliminated E, that's not going to help as much as x equals -1. But this is kind of the typical multiple choice problem, match the equation to the slope field, match the slope field to the equation, something like that. And that's all I got for you for this video.